going to take a look at lines and planes in space. And we're going to start with lines. All right. As with lines, in a plane, we can specify a line by identifying two points on a line. Or 1 point and the direction of the line. Now in 2 dimensions, that direction of the line is what we call slope. It's a little more complicated than that when we're working in 3 dimensions, so we can't call it slope. But we'll talk about what we do instead. So we have 2 ways to represent the equation of lines. In space. And those 2 ways are parametric which we have seen before, and then symmetric. And we'll see how symmetric comes about from parametric. It's pretty straightforward. So let's talk about parametric first. So if we have parametric form of a line, what it ends up looking like is it looks like we have 3 equations of lines, okay? So x will be x1 plus a1t. I'll define what all these are coming from in a minute. Y is y1 plus a2t. And z is z1 plus a3t. Now, each of those individually look like a slope-intercept form of a line, don't they? You've got what looks like it's probably a constant. You looks like what it might be operating in the way of slope, and then you've got some variable t that's going on, much like y equal mx plus b does. And in fact, that's exactly what's happening. So this is for a point y1, excuse me, and z1, so that's our point. And instead of slope, we actually have a vector indicating our direction. And our vector, we'll call it A, has components A1, A2, and A3. So the direction, the change in each of the 3 directions for A1 and A2 and A3. Now, that's parametric. It feels so much like the equations you're very used to in 2 dimensions. Symmetric looks like this. So for symmetric, we end up with x minus x1 over a1 equals y minus y1 over a2 equals z minus z1 over a3. Can you tell how symmetric is related to parametric?
They all solve for t.
Yeah. If you were to take each of the parametric equations and solve them for t, the t has to be the same in all three, then each of those three would be equal to one another. So it's eliminating the parameter is what it's doing. Okay, so that's a symmetric form of a line. So we're going to start by doing an example of finding just exactly this. So our example says the following. Find first parametric and then of course second B symmetric equations of the following. So, whoops, it's example number 1. We have the line through, and we're given 2 points. Okay, so think back to what you do in, algebra, like algebra 1, maybe even pre-algebra the very first time. You're given 2 points and you're trying to find an equation of a line. So you have a point, that's fine. We need a point for either of these particular forms of a line. We've got the point, we've got 2 of them. But we would typically, in 2 dimensions, need slope. And we'd need to be able to take our points and create the slope from the 2 points. So we're going to do the same thing here. We're going to take our 2 points and we're going to create the directional vector that we're talking about, A1, A2, A3. And you know how to do that because we've done that before. So we're going to start by creating our vector, right, finding the direction. And it's simple arithmetic, right? We're subtracting, and it doesn't really matter which way do you subtract. I'll do the second one minus the first one. So I'd have 2 minus 0, and then 0 minus 2, and then 2 minus 1. You certainly wouldn't have to show those out, but that's where they're coming from. This gives us 2, negative 2, 1. And this is our vector A. Is that all right? And now that we have the components of the vector, and we can choose either point, let's just decide to choose the first one. Not because we have to, but because we're going to do the same thing. And this direction right here, we can create the parametric and the symmetric forms of our line. So parametric means I'm going to have x equals, and it's x1, which is 0, plus a, which is a1, which is 2t. You don't necessarily have to write the 0, of course. The y is 2 minus 2t. And then z is 1 plus t, or 1t. Is that good? All right, so somebody tell me what you're going to end up getting then for the symmetric form of the line. Okay, do we agree with Caleb? Yeah, I do too. So if you take each of the individual parametric equations and you solve for t, you can think of it from that perspective. If you want to actually go back and see where the pieces are coming from and look at the equation that we created over here, you can come at it from that perspective. And either way, you end up with that as the other form of our line. Yep, Hannah.
Does it matter which point you use? Like if they give you 2 points, or is it like?
Nope, it doesn't matter. You can use either one of them. It happens when we do equations of lines in 2 dimensions as well, that when you break them down in certain ways, they end up being the same thing. It's the same stuff, yeah. Doesn't matter, not at all. All right, any questions about that? Okay, so let's talk about the relationship between different kinds of lines in space. So much like in 2 dimensions, we can talk about things being parallel, and things being perpendicular, being intersecting, and we have a third one that's going to show up in all of this as well, or another one that's going to show up. So we're going to say let L1 and L2 be lines in space. With directions A and B. So for starters, whoops, L1 is parallel to L2 when vector A is parallel to vector B. Not only that, but we talked about what happens to get parallel vectors. What does parallel vectors actually mean? Do you remember? Yeah, they're scalar multiples. We'll get to that part in a minute here, Annika. So, i.e., if it helps us to remember, A would have to equal C times B for some C, right? It's a scalar multiple. So that's parallel. The other option here is that they intersect, for the moment anyway. I think, oh yeah, it's going to break it down here in this definition even. So if L1 intersects L2, then the first option is the angle, or not the first option, but the first detail is that the angle between L1 and L2, namely theta, is the same as between A and B. And that should make sense. And then the second detail here is if lines L1 and L2 are orthogonal, not if, the lines, sorry. The lines, L1 and L2 are orthogonal, when A and B are orthogonal. And how can we decide if two lines are orthogonal? Do you remember? Or how can we check to see if they are? Not lines, but vectors. Sorry. Yeah. So this happens when A dot B is equal to 0. So we're looking for things that are scalar multiples and for dot products of 0. That's what we're looking for when we're trying to decide these facts. Are you ready? Have we got that? Okay, good. All right, so our next example is to find exactly those details. So we're going to determine whether the lines are parallel intersect, and in 2 dimensions those are our only 2 options, but in a 3rd dimension we have one more option, which is that they could be skew. Let me finish writing my directions, then we'll talk about skew for a moment. If they intersect, we're going to find the intersection point. Okay, so in 2 dimensions, lines either cross or they don't. And if they don't cross, they're called parallel, and that's just all there is to it. Well, in 3 dimensions, they either cross or they don't as well. It's just that when they don't cross, there's 2 different things that could happen. So imagine our classroom that we're in, and we can talk about parallel lines using the walls and the ceiling and the floor of our classroom really well, because you can see it. So my wall behind me, that's going to be one of my planes. The top, the ceiling, and the floor are going to be another couple of planes, okay? So the line that connects the ceiling and the wall up here that goes along the top of this corner and the line that connects the floor to this wall, those would be parallel lines, right? If they continued indefinitely in either directions, they would never cross one another, okay? But they're also sort of this equidistant idea, okay? If I took that same line that's at the top of my classroom, but instead of using the line at the bottom over here, I talk about the exterior wall to my right and the floor over here, there's another line that would go across the bottom of the floor. That line doesn't cross the one up at the top either, but they're clearly not parallel. Those would be called skew lines. So they don't cross one another, but they're also not parallel. So we have that as an option in 3 dimensions, and we didn't have that as an option when we were looking before. So we're going to take a look, and this directions make it sound like you have to make the decision and then find the intersection point. That's not really the way it works when we're doing it. What we're going to do is we're going to be looking for an intersection point, and if we find one, that's the one, and it's an intersection point. And if we don't find one, then we won't have one, and then we would have to decide, are they parallel or are they skew, okay? And in fact, it's very easy to tell if something's parallel. We talked about it over here. They're parallel if they have the same direction vector, or at least scalar multiples of it, right? And so we can see if something's parallel very quickly, and then looking to find the intersection actually will determine for us whether there's an intersection or whether it's skew. So it's not like we're working in this sort of like, does it intersect, does it not? And therefore, now that it does not, is it parallel or is it skew? It doesn't quite work like that. Okay, so let's take a look at an example. We'll get some values in here. And this one is actually given to us in parametric form. So x is equal to 4 plus t, y is equal to 2, and z is equal to 2t. So that's one line. I know it looks like you've got 3 things written there, but that's the form that the line's taking. The other one is x equals 2 plus 2s, y equals 2s, and z equals negative 1 plus 4s. So we can actually first figure out the direction vectors, and we can decide, is it parallel? That's the quickest thing to do. Because if it's parallel, you're going to know really quickly, and you don't need to find anything else. The parallel is the easy part, okay, determining that piece. So let's find our direction vectors. So we'll call this first one A. So what is the direction vector for our first line that we're given? 1, 0, 2. So notice on y equals, there is no component t, so that's a slope or a direction of 0. And then how about, we'll use B for the next one. What about the direction vector for the second line?
2, 2, 4.
Okay, is everybody good on finding the direction vectors? Okay, look at those direction vectors. Are they scalar multiples? No. And in fact, because I've got a 0, I can very quickly decide they're not scalar multiples because they would have to both have a 0 in that second component, right? And they don't. So that actually tells us that these are not parallel because they are not scalar multiples. Okay, does that make sense? Not scalar multiples that don't have parallel lines. Okay, so now we got to decide, well, is it skew or is it intersecting? And again, like I mentioned, what we're going to do is we're going to attempt to find the intersection point. If we are successful, it intersects. If we are unsuccessful, then we're going to know that it doesn't intersect and it's skew. Okay, so how do we do that? Well, what we're going to try to do is we're going to try to eliminate some parameters. So let's take a look at the first x and the first y. So if I take a look at my first line's x, I have, I'm just going to put a dot next to it. It's 4 plus t. And my second line's x is 2 plus 2s. Is that okay? All right, if they're going to intersect, they have to have the same x coordinate, so I set the two x coordinates equal to one another. Now, obviously, I have 2 variables, a t and an s, and I need to know if the t and the s, like if there are a t point and an s point that's actually going to work for this, that also works for y and for z. So let's do y next. And y is actually very nice to do. Any idea why I'd like to do y and not necessarily to do z, although I could do z? The second one's very nice. It can solve for s directly. So with the equation for y's, the equations given for y, I only have the variable s. So it's very easy to solve for s. What would s equal? Yeah, S is 1. So if S is 1, I should be able to take that and put it back into the equations that I set equal for X above. So I would have 4 plus T equals 2 plus 2 times 1. So can you solve for what T would have to be? T would have to be 0. Okay, so I have a location now where they have the same X and the same Y. That's what this is that we just found, right? I didn't write down what the X and the Y are per se. I found a T and an S that satisfy X and Y being the same because I set them equal to each other. What I need to see is if the Z component's the same at that location. If it is, they intersect. If it isn't, they're skew. Okay? So if I take the S equals 1 and the T equals 0, and I put them into the equations for Z, the question is, do I get the same Z component? So if T is 0, then on the left-hand side, Z equals 2 times 0 would give me 0, right? That's a little too high up. Let me move that down here. So this is the left equation, right? Like L1. I didn't give them these names, but let's do it now. L1. And here's L2. In L2, if I put in the S value, I would have -1 plus 4. S is 1. Is that what I got? Sorry, just a second. There's something weird in my notes. Okay, I think I just have a typo in my notes. Sorry. Okay, I think I turned it back on. Okay, so what do I get for the Z on this one? 3. Are they the same? No. So these don't match, right? These are not equal. So what does that tell me about my lines? They are skew. Okay, if they had matched at that point, that would actually be the Z coordinate that I would need. I could go back and I can get the X and the Y coordinate to make them the same too, right? Because I'd know that S is 1, T is 0, and in both the left line set of equations and the right line's set of 3 equations, I would have had the same X, Y, and Z ordered pairs. Any questions on that one? Okay, so this is lines. We're going to shift now to planes. Okay, a plane in space is determined by specifying a non-zero vector. And we're going to call it n. We're just going to put its components as A, B, and C. And we're using n because this is called the normal vector. So it is normal, not as opposed to abnormal. Okay, normal to the plane. Have you heard or seen the word or phrase normal or normal to the plane before? Linear maybe? Does it happen in there? Not sure. Normal means that it is orthogonal to every vector lying in the plane. So we've got this normal vector and a point. x1, y1, z1, lying in the plane. Its equation is a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. Or, it's kind of like what we do with other things when we have lines as well. We'd like to multiply things out, clean them up so there's not all the parentheses. So if we do that, there's an ax, a by, a cd, so that's not right, cz, and then plus d equals 0. So d, we don't know what that is. It's the combination of all the other, constant pieces that come about from the equation above. Okay, so just because something's orthogonal to one line in a plane doesn't mean it's orthogonal to all the lines in the plane. But if it is, then it's called the normal vector. All right, I think we've got space enough on there, so let's give it a go on this slide. We're going to find an equation of the given plane. And this is the plane containing points 1, -2, 1, 2, -1, 0, and 3, -2, 2. It doesn't specify like names of these points, but it's going to be helpful for us to include them. So I'm going to call this one P, this one Q, and this one R, but feel free to use any letters, it doesn't matter. Okay, so what we're going to need is we're going to need some directional vectors. So we're going to take vectors, take 2 of these at a time, and we're just going to go in order. So we're going to find vector PQ. All right, so work with me. What do you get for vector PQ? Yes, it is 1, 1, -1. Good job. And let's do PR. Two, 0, 1. Okay, are we all good? Okay, we need to find an orthogonal vector to this one, right? Or we need to find the orthogonal vector to both of these ones, right? So we found 2 vectors in the plane. So imagine we have 2, vectors in our floor. And we want to find a third vector that is orthogonal to both of them. And if it is orthogonal to both of them, it will be orthogonal to the plane that the floor is creating, okay? How can we find an orthogonal vector?
Cross product.
Cross product is it, yes. Okay, so we're going to, and I'll slide this to the next slide since I'm out of space now. We're going to find the cross product of these, and we're going to set it up. We haven't done that actually together in class since you had a video just to watch on that. So we will set it up all in full. We're going to do PQ, and we're going to do the cross product with PR, not QR, PR. So when we were setting this up, you guys did things with some determinants, right, for matrices. And if I'm doing the I component, I'll use the second and the third. So I have 1, 0, -1, 1. I have minus the K component. I'll have my first components, which is 1 and 2, and then the third.
You mean J?
Oh, sorry. Yes, I do mean J. Thank you, J. -1 and 1. There I have my K, and I'm going to go back and put my hats on them too. So I didn't have those. And then for k, I have 1, 2, and 1, 0. Does that look all right? All right, so we're going to find these values. Some of them are going to be zeros. That happens to us sometimes. And so when we look along the first diagonal, 1, 1, and then the other one's going to be 0, so I actually end up with just I. Find the determinant for the second one. So if you come down and then you go back up, what are you going to get? 3. And the negative in front of j is going to make it a negative 3. Right, because of the negative right here. And then we'll do the same thing over here for k, but this first diagonal is 0. So what do I get for k? Negative 2k. So this vector is normal to the plane. If you want to write it in the coordinate form, you would have 1, negative 3, negative 2. Either of these forms is normal to the plane. And then we're going to be able to write the equation of the plane. So this is the equation that we had up here. So we have the normal vectors, first component times x minus the x value, and so on. So we have our value of 1. Then x minus our x coordinate, and I'm just going to use the first point P. We mentioned before it doesn't matter. I'm just going to go with the first one, so it's minus 1. Plus our second component, our j component, which is negative 3. And then I have y minus, and the y value is actually negative 2, so it's y plus 2. And then my j component, which is the negative 2. And then z minus the z value, which is z minus 1. So this is almost something like, you know, the point slope form of a line, kind of a feel to it, right? Because it's in these coordinate, or these ordered pair kind of, not ordered pair, but these parentheses components. If we distribute things through, I have x minus 1 minus 3y minus 6 minus 2z plus 2 equals 0. I have x minus 3y minus 2z. If you collect all the pieces, right? So I have negative 1s, negative 6, and positive 2. What are you going to get? Negative 5. And this would be the equation of my plane. All right. Our next one is going to involve a little bit of graphing. You guys know how good I am at that. So I'll at least give you some kind of an idea of what would be important to have plotted for some visual purposes. So we're going to find all intercepts. That's fine. We can do that. Intercepts and sketch the graph. That's a little less fine, but it'll be okay. All right, and our equation is 2x minus y plus 4z equals 4. Okay, so thinking about what you know about lines in 2 dimensions, if you want to find the x-intercept, how do you do that?
Set it to 0.
You set what to 0?
X. The upper 2.
Yeah, so if we were doing lines and you wanted to find the x-intercept, right, in 2 dimensions, you'd let y equal 0. And if you wanted to find the y-intercept, you'd let x equal to 0. So you're already 3-dimensionalizing it for me, Caleb, but you're exactly right. So if I'm wanting to find the x-intercept, I'm going to let y and z equal 0. And the same thing for y and for z. So when we find our x-intercept, what it means is that y is equal to 0 and z is equal to 0. So I just have the 2x, it equals 4, so x is 2. So this is the ordered triple 2, 0, 0. Y-intercept, I would let x equal 0 and z equals 0, leaving me with only the y component, so negative y equals 4. So this one is y equal negative 4. So I have 0, negative 4, 0. And then our last one, our z-intercept, is x is equal to 0 and y is equal to 0. So I end up with just the z component, which is 4z equals 4. So z is 1. And this ordered triple is 0, 0, 1. Is that process okay? Okay, we can graph that as well. That's not too bad. We can graph those 3 points. So let's sketch that. That's valuable, and it's something that's pretty straightforward to do. So we're going to graph in 3 dimensions, something like this. Remember, this is x, this is y, and this is z. So we're on each of the axes, so that kind of is nice. The x-intercept is 2, 0, 0, so that's something along the lines right there. The y-intercept is at -4, and in order to draw that, what do I have to do? You have to kind of go opposite, right? So if I'm drawing this, I think that's pretty okay, mostly. And I need to go out 4, so I need the distance to sort of look the same, something like that. And we would have this point here at 4. The z value is 0, 0, 1, so I'm going to go straight up from there. That's not even straight, not even remotely straight. And it might be a little bit better. Okay, so 1, and we would be right here. Okay, so you should be able to plot the 3 points at the very least, and it make it look reasonable. So the way that we're going to connect those 3 points is we're going to connect the 3 points in a triangular shape. And you're going to imagine the triangular shape continuing on, of course, indefinitely in all directions, because graphing a plane is a little difficult anyway. So I'm going to draw them in as dotted red lines. Maybe I won't use red. It's kind of running into the dots I already have. Let's use blue. So it looks something like this. This is the plane. You can imagine connecting those 3 points and then continuing on in each direction. So you may not get the visual feel that you wished you would have had. Maybe WebAssign will do a better job for you. I don't know. But this is about as good as I can do, at least when I draw it. Okay? So you don't have any higher expectation than what you can see me do. How's that sound? Good? Awesome. All right. We have one last example. We are going to state if the lines are parallel, perpendicular, which we talked about earlier, we just haven't done it, perpendicular, or neither. And the lines that we're going to work with are given again in parametric form. That was not good. Let's try that again. A little bit better. X equals 1 minus 3t. Y equals 2 plus 4t. Z equals negative 6 plus t. So this one is we will call it L1. And then our second line is x equals 1 plus 2s. Y equals 2 minus 2s. And z equals negative 6 plus s. And we'll call it L2. Okay. What would we do first to decide if it's parallel? This isn't anything we haven't already done. Yeah, we would want to look at those directional vectors and see whether or not they're scalar multiples. Right. So what is the directional vector? And again, I'll call them A and B because that's what I used before. So what is the directional vector for line L1? Negative 3, 4, and 1. And how about the directional vector B for line L2? Okay, just that information is enough to decide is it parallel or not. And Annika's shaking her head no. How come, Annika?
There's no scalar.
Mm-hmm. There's no scalar multiple. So they are not scalar multiples. Okay, if they were, we would be done and we'd be happy to move on, right? So don't do more work than you have to. Check them because if they are, you're finished. So how do we decide if they're perpendicular? Well, I want to show you another way to decide if they're perpendicular because it gives us a little bit more information than what we did before. We talked on the other section, like in the earlier part of this section, of how we could decide. What could we do? We could do the dot product. I want to show you another way that we can decide. So we had a formula that related the angle measure, cosine of theta, to this. So the cosine of theta is equal to the dot product of A and B divided by the magnitude of A times the magnitude of B. Remember that? So while the dot product could tell us for sure, right, and if the dot product were 0, we'd get 0 on top, and we'd find out very quickly that the angle would have to be 90 degrees and so forth. That's fine, but if it's not orthogonal, right, or if it's not perpendicular, then we're kind of left without any kind of information. This will actually tell us the angle measure between them as well. So we're going to find an angle measure on this one. And the angle measure won't be 90 degrees, all right? Because I want to show you that you at least get a little bit more information when you do it from this perspective. All right, so we're going to do these three pieces. This is A dot B, magnitude of A, and magnitude of B. So A dot B, I'd have -3 times 2 plus 4 times -2 plus 1 times 1. What is the dot product value? -13. All right, magnitude for A. I'm squaring each component, and because I'm squaring, I'm going to ignore signs. This is 3 squared plus 4 squared plus 1 squared, which gives me what? And we'll do the same thing for B. This is 2 squared plus 2 squared plus 1 squared. Yeah, it's the square root of 9. So this one's actually the whole value 3. That didn't happen yet, right? We've got that one happening this time. So if we are looking for the angle measure, because that's another version of the type of question this could be asking, not just is it perpendicular, right? We could say then the cosine of theta is equal to -13 over the square root of 26 times 3. And how could we find the angle measure?
Arc cosine.
Arc cosine. So we'll take theta, we'll do the inverse cosine or the arc cosine of -13 over 3 square root of 6. Making sure you're in radians. This will give you approximately 2.59 radians. And if you had sort of stalled out and forgotten the whole dot product thing we had talked about before, what you would be looking for here is you would be looking for it to have the angle measure of what? What would it be to give you a 90-degree angle? Pi over 2, right, pi over 2. So about 1.57, right? Pi over 2 is what we would be getting. So the fact that I don't get that here means that it's not perpendicular, which we would have already known because the dot product wasn't. But if we were asked also to find the angle measure, we'd have that as an additional piece of information from this particular process. Okay, let me flip to the next page. We'll get you some homework. It's not very long. It is page 794. 7, 10, 30, 31, 34, 35, and then 46, 47, 79, and 82. So considerably shorter than a few of them we've had lately.
Longer than the last one.
Longer than the last one, so sorry.